Alright, so here we want to prove is the following. That diamond equal to n times q be greater than 1. Then every mean between 1 there exists delta, which will be a function of both mu and lambda. Then 0. Such that this is the punchline. The probability that largest connected component is this is my n. There will be also eta, so this term will be again. This is 1 minus eta, the extinction probability of the corresponding binomial branching process. This is 1 minus eta. Eta was our extinction probability. This is the survival probability. So yes, the F difference will be greater than L to the nu is order L to the first. Is the statement clear? Yeah. What are we asking? We're looking at the maximum connected component. This quantity is n times the survival probability of the branching process with expected number of progeny lambda. Saying essentially this is very close to that. That's all is. All these are just small components. We're controlling the probability that the largest connected component deviates from this. This number is nothing but the expected number. What is this number? Can you reinterpret this number?
Size of the
No. The expectation of something. See, this is the survival probability. The survival probability times the number of nodes. What does it mean?
like a particular level, how many signals are there? No, oh, sorry. N is the number of nodes, right?
It is the
Expectation of nodes.
expectation of what kind of nodes? See, this is survival probability of a branching process with Poisson random variable lambda. If I multiply this with n, what interpretation can you get?
Like active nodes. Right? No, these are the number of nodes from which the new branches will come out. Right?
This is the probability with which what happens in the branching process
The probability
of not extinction.
yes.
So for a particular node, what does it mean? Essentially, that its progeny keeps going.
Yeah.
That's one. And this n is from the Ardoshrani graph. So if I multiply this, what is the interpretation you can make? It's the number of nodes which have very large connected. It's not exact, but that's what you can essentially use. What is this epsilon delta? Is the probability that I have an unlimited number of progeny. In our language, what does it mean? It is somehow connected to the largest component. So what is the probability that a particular node is connected to the largest component? And n is the total number of nodes. So this is nothing but the expected number of nodes which are connected to the
Largest component.
It's saying that this is actually close to that. That's what the statement is saying. That the probability deviates beyond this, that will be very small.
What is the gamma?
For every gamma between half and 1, this is 2. So gamma is a variable you can choose between half and 1.
That is n to the power gamma, right?
Yeah. So we will call this mu. So this interpretation clear what we are trying to do.
So this the probabilities of the order of
10 to the minus delta. It is degree. So with high probability, this is true.
no okay,
What is this greater than equal to? So this is telling you that the probability that it deviates from this number. Larger than this is small.
small, yes.
That's all. Okay. So the high probability is actually close to. With a tail bound you can like this. Typically probability is called a tail bound. What is the probability that the random variable is greater than something? If it could diminishing significantly, that's what your tail looks like. So this is what we want to do. So what does it like if you just look at such a statement, what does it tell you about the connected component size? Yeah, that's all it's telling. It's order n. So if somebody provided you this statement, what would you conclude about the size of the connected component? That's C max. How large is C max with high probability? We already seen that if lambda was smaller than 1, this is roughly or rather maximum is log n. You can't get more than 1. Suddenly, as soon as it shifts beyond 1, you're able to get something which is growing as habits. So this is what the phase transition is. It's precisely that boundary. Lambda less than 1, you have log n. Lambda greater than 1, you have everything you want. At 1, it's difficult. All right, so shall we go ahead and prove this? It's going to be, it's not difficult, it's just long. That's it. But
this branching process is
so epsilon lambda survival.
with lambda is empty and this P is of the heterogeneity process.
Right, so this is L time. Survival probability of horizontal. Make sense? See, we typically compare against a binomial, creating one more step. So we already seen in the past homeworks as well as classes that binomial is close to person. We're jumping. So there is a adversarial graph. It looks closer to the binomial branching process. We're making one more step and going to the Poisson branching. Proof also you will see. First comes the binomial, then comes another level from binomial to Poisson. All right, so shall I embark on the proof? So strategy. We are going to do, then we will wait. We'll see if we can finish today or not. Okay, so this is the relation. This will be. Let me just see this capital is one indicator function. These are all the nodes whose connected components is greater than k. Z greater than. There are nodes. Each node has a certain number of connected.
It's basically this V, whatever this thing is, it's basically counting the number of nodes
which have their connected components larger than size of their connected component between k. They may not be the same.
Yeah. So it's a check function for all the nodes.
Yeah, for every node, it belongs to the graph. I'm just checking whether its connected size of this connected component is greater than k or not. Every time it is greater than k, I put a 1. Otherwise,
Yeah.
So step 1. This is the something maybe no again where k will be large. So what is the expected value of Z greater than K? It's simply n times. So each individual node has the same distribution with respect to its size of the connected component. So I can simplify it. Or rather, I can put one here. But let's. So I could use Kn rather than K. Eventually, I'll put Kn. So this is true for every K. In particular, it's true for Kn. So that's what I'm going to use. This is true, right? What is the expected value of an indicator? It's exactly the probability it takes from long. That is exactly it. So now this is the probability you want to control. What can you say about it?
What can I say about this probability?
As a function, let's say, as a function of pure survival probability of the Poisson fraction process.
No, I have to map this probability in
No,
terms
I want to have some relationship between this and the survival probability of my Poisson branching process. You don't have to compute, just make any observation and everything. I don't want to derive anything. If you remember the definition, what is this? This is just the size of a connected component of a particular V to be greater than K, and where K is capital K log n. In another side, I also have a Poisson branching process, the survival probability epsilon n, where everything like n times Pn is the same. That's when I can compare. What do you think is there any relationship between the two? At least intuitively. What is this telling you? That this is sufficiently large.
Yeah.
So what should be an obvious relationship between this and the survival probability? Survival probability means that the number of progeny is large enough.
Yeah.
This is saying the connected component is large enough. So there should better be some relationship between the two.
So you can ask me like how like bound or something.
You can give proportionality. I don't want absolute answers. Can you even suggest some proportionality between the two? If this is large, what has to happen to that? Remember, we have domination. If you remember this. That our actual the process on the Ardoshreni graph is both lower and upper bounded by Poisson branching process. So if this is growing large, what do you expect that to happen? That also should better go large. And what is the probability that that goes large? Is epsilon n. So you would expect some relationship between this. So in step one, what we show is that this is in fact equal to little over one is just something very small. That's all. All those terms will be counted over there. This is what step one will show. And we have actually shown everything in the last classes. All I will do is to recall those theorems and put it. But the intuition is that if this is large, it better be that the Poisson branching process also grows sufficiently large. And the probability of that happening is nothing such now. All the other extra terms will be just combined out. That's your step number one. Oh, now step number two. This is more important than the actual process. That if you are after something like this, how should you proceed? If you can narrow it down to say, I want to show this, I want to show this, I want to show this. Showing individual steps is not very difficult. But seeing through the proof that what needs to be proven to show this, that's more important. So if you break this down into step 1, 2, 3, 4, I can actually give it out to you in homework and you'll be able to complete those steps. But more important is actually see through what. Okay, so now the next step we want to do is to show the following, that with higher probability that greater than k minus the expected value of the same quantity. Yes. Can you put a bound as a function of pick any new belonging to 1/2 only? This is a random variable. This is the expectation. What do you think typically happens between a random variable and expectation? What is the probability that it deviates by a sufficient amount?
Standardization must be large, right?
No, just think of big law of large numbers. A random variable deviates from its mean, the probability of that happening is how much? It's pretty small. And how small? Depends on how many random variables you're putting.
Yeah.
So as n grows large here, this better come closer and closer. You see, big law of large numbers. What is this stated for function for 1/n summation x(r). So all of these are identity minus the expected value of x greater than a is also for any a.
Maybe it's still with 1 by.
Yeah, a by n. Root n.
Not root n.
People at home who remembers weak law of large numbers? I'm pretty sure Pranav is on top of it. Pranav, what's the formal statement of weak law of large numbers?
The sample mean of n.
I've written everything on the board. Just give me the right hand side quantity. What is the probability that the expected value of x is different than the sample average with n samples? How does it
It's
decrease?
very small, like
No, how small? How does it decay with a and n? You can see the screen, right?
yes.
Yeah, so tell me as a function of a and n.
Then ex expectation value minus a by.
A by n. A by n. Is that correct? At least n is okay, but should this increase with a or should it decrease with a?
Decrease, right?
But this is increasing.
Yeah.
So switch over, but at least you should brush this up. And not writing it because at least you go home. And so what is essentially means is that this is a random variable, this is the expectation, it better be small. What we'll try to show is that this is gamma n to the with high probability. Strictly less than otherwise makes no sense. This is what step 2 is. See, what are we doing? Step 1 step at a time. We have somehow written this as the number of vertices which have a connected component larger than this. This we are connecting to the survival probability of the branching. Now at the same time, I also want to know how is this deviating from its expectation. That's what step number 2 is. Now can you fill up saying where am I going in terms of trying to prove the theorem? Okay, so that's typical what you're trying to say. See, this to this to this. These are connections. This is a random variable, I don't know how. Expected value is this. And this is close to its expected value. So essentially I can go from here to here. That's what I've done so far. In 2 steps. What more do I need to do to actually control the event I'm interested in? Now, how is Z greater than K related to What I'm after the size of the maximum.
Yeah.
C max. What is C max?
No, I think
Is there any condition under which C max has a relationship with Z greater than K or Z greater than Kn? So suppose I tell you that there is no connected cluster of size less than equal to K log n. Then can you connect Z greater than K with the C max?
there is no, sorry,
There is no connected component of size less than K log n.
okay.
So then can you connect C max with Z greater than K log n? Just look at the definition.
I mean, I think
What does it include? It includes everything above K then.
Mhm.
If I'm telling you there is nothing below,
all the means this the total sum, right?
Yeah.
It will be zero.
no C max.
Means the max, right? Yeah, it's zero.
So Z greater than Kn should equal C max itself. No? Let me write it more. So this is step number 3. What we want to show is that again Kn is K log n. For enough K. We want to show it the probability that connected component of vertex is greater than Kn and less than alpha n. K is smaller than K minus Kn times J. Think of J as a system. And alpha is any item. Just stare at this for a moment. What is it telling you? Suppose this is true. What does it mean? For any V.
So it's telling you
There is a constant.
okay. The probability of the connected component of any node being in this range.
Yes. It's very small. So with high probability, either they are smaller than Kn or bigger than alpha.
Yeah.
Okay. So suppose I give you this also. Now can you relate Z greater than Kn with the C max?
So if you put in the place of alpha and let's say C max.
What does it mean?
It means the probability of I mean like a node in a cluster of okay, so
And remember alpha is 50 less than epsilon.
hmm.
Xi.
Yeah.
For my connected cluster, I want it to be this times n.
Yes. Yeah.
So this is actually smaller. But all is telling you that the connected component of any particular vertex lying between these two sizes has very small probability.
Mhm.
Now suppose this has very small probability, assume it's 0 for example. What can you say about C max and Z greater than K? Is there any relationship between C max and Z greater than K? That's all we are. By definition, what is Z greater than Kn? All nodes which have connected size greater than capital K times log n.
Yeah, if there exists a grand component, then it's order n.
What?
The E greater than
The number of components in Cmax will be equals to Z and
Sorry, say it again, slightly loudly.
the number of components in Cmax, the number of vertices.
See, Cmax is a single component, right? By definition, Cmax is the size of the or the largest connected component. So it is a single entity.
Means the number of vertices in that component will be
Yes.
equals to Z.
Right. So that is mod Cmax.
Hmm.
So what do you want to say about it?
Uh, no. I was thinking of something else.
Okay. So what we will show. Yeah. So suppose this is true. We'll show each of these steps. What does it mean? This is very close to its expectation. This guy is close to epsilon n. What does it overall mean? That Z greater than K log n is close to what? Its expected value.
No.
1 is 2, 3. Combine this. What does it mean in terms of the random variable itself? If this is close to its mean, mean is close to the epsilon n.
Okay.
So what is this close to?
This
Now, given that we know this, and we also know this relationship, what can you at least guess as a relationship between Z? So think a little bit. What is it essentially telling you? That there are no clusters of size. What does it mean? So either is above.
Yeah.
So if I pick an alpha which is greater than this, I'll most likely find every. See, there is nothing. So if I start at Kn, anything below there is anyway nothing there. Up to this time there is nothing.
Is it below Kn?
If I start at Kn, I'm not comfortable. These numbers are going like this. Kn and increasing. I'm counting everything above Kn. But I'm telling you at the same time that between this and this there is nothing left. So what is this part?
Yeah, so there might be a cluster, or below K there might be a cluster. I mean,
Okay, fine. There are clusters of this side, agree. There is clusters above it. What is the relationship I can, because I'm going above it. So what lies above? Below I am not even counting. In my Z greater than Kn, I'm not counting these guys.
yeah, so above this, I think there will be Cmax, right? I mean,
So tell me a relationship between the two. See, what is there? This split probability is 0. This is happening, correct? Until alpha n. So if I start counting cumulative sum starting from Kn, anyway there is nothing to be counted between here and here. So what am I actually counting?
Okay, after
See, I don't have a good handle directly here. So that is why I'm going via this Kn. So ZKN is counting everything in this region. I'm going to count everybody here.
N tend to infinity limit, it will tell you the existence of
Whatever exists. What is the relationship between these two? That's all.
okay.
Because how large is that Kn, we'll worry about it later. That is going to come from something else.
Okay.
All I want is the connection between the two.
In
So what is that Kn? It's going to count. What does it count?
That can will count the
This guy, plus this guy, plus this. But I'm telling you that there is nothing here. So what is it counting? It's exactly counting things above.
After.
Right. So what does it have a relationship between C max and ZK?
There will be a particular this K, right, for which.
By definition, what is C max? Largest cell.
Yeah.
What is its relationship between ZK? That's all.
If that K is one, then.
Why one?
One is.
What is the definition of ZK?
So ZK will count after alpha, and that's what you are saying, right?
Exactly this. Even though I'm including all these guys, there's nothing there really. So what am I counting? Everything above. So what does it imply? How, if whatever that number ZK is, what is, does it have a connection with C max? One direction is easy. Okay. Don't condition it on the fact that there exists a that component. So if I tell you that Z greater than 10,000 has probability 0, what can you tell me about connected C max?
Again, what?
Probability that Z greater than 10,000 is 0.
Okay.
What can you tell me about the connected component of this graph? It is at most 10,000.
10,000.
There is some relationship between Z greater than K and C max. So give me at least one direction. You can assume that it's close to its expectation. What is the expected number of ZK?
So,
C max is actually.
Okay, now we are at least able to connect those two quantities. That's why we are harping on the fact that assume that Z is close to its expectation.
yes, I mean, you can do.
What is the expected value of that?
If you put C max instead of K in this definition of Z, then Z of Z C max is basically C max, right?
What do you want? If you put K as C max, mod C max.
Yeah.
Okay. Then what will happen here?
So,
Their expected value is nothing but the total number of nodes which are part of the connected component. Now we know what is going on. What is the connection between ZKN and C max, given that there is nothing in between?
the expected value is, if there is nothing
In between.
C max is at least alpha in it.
What if the probability of that happening is true? Then yes,
Yes.
correct. But nobody told you that it does actually happen, right? Yet. I have only told you that this is true. I have not told you that CV greater than alpha also is not trivial. That could also be 0.
This is true for any K, and I can.
For large enough K, that is true.
For large.
This much is given to you. So there is something left which is being counted in ZKN. What is that something? As a function of C max. C max is at least as much as that. At least you should say that. Right? So C max, this relationship should be obvious.
Yeah. Can I just multiply it by exponential?
No, but is this okay?
Yeah.
So why is it not sufficient for us? Anyway, I'm controlling this random variable. And if I can show that this is large enough, then automatically C max is large enough. And that is what I'm really after.
Yes.
We'll show actually something stronger, that it's actually with high probability they're equal. But this relationship is more or less what we need. Because this is the random variable I'm going to control. Just to recap again, so make sure that we understand what we are doing. Each of these steps are not difficult at all. We're looking at all the vertices whose connected components are greater than. This has, supposing that this is close to the expectation, which is going to have a high probability. This will, think of this as replaced by this quantity. Right? This is what this is. So just don't even think about it. Just think about this quantity. What does it mean? N times the probability that the connected component is greater than K. Now, what does this has to do with the Cmax with all you have to worry? This is not useful unless I show you this. If there is vacuum in large particles. So from log K to some constant times N, there is actually nothing there. So if there exists something, then the connected component better be of the size greater than alpha n because of this relationship. That's all we are going to do. So this is really the key step to observe, not to prove. Prove is actually easy. So are we okay with what we're going to do? You'll be surprised, each step is not difficult. If I were to say what is the most non-trivial step to visualize before we begin the proof, this is the non-trivial. To show that the probability of a connected size of a connected component being larger than K log K and less than alpha n. See, what is it telling you? That either the connected components are of size log n, or suddenly there is a huge jump. This is something you should observe. And that's why you'll be able to show that this connected component is also unique. If there are lots of these small guys, they would possibly have multiple connected components. The giant component was not order-wise n, it was smaller. Possibly could have two distinct ones which are not connected to you. What is telling you there is nothing, there is vacuum in the middle. Either they are very small of order log n, or they are order n itself. There is nothing in between. That is what the most non-trivial step is. Okay, guys, at home, is it clear what we are trying to do?
Now,
Yeah.
if suppose there is no giant cluster,
We are not conditioned on anything yet.
suppose
The whole point is to show that there is a giant.
take the case where we do not have giant component, we have
See, once you condition, everything changes. So that's why you have to be very careful. If I put a condition somewhere that there is no giant component, all these probabilities will completely change. If you want to say something, say something. So intuition you can build, but once you condition on the fact that there is no giant component, what essentially everything should correctly compute to that all the connected size components are of order log n. That's what this is actually telling you. That if there is no large enough component of order n, then the next size you should find is only log n. That's really what is going on. There's nothing in between. There's no square root n, there's no n to the power 1/3. That's what the punchline really is. And that's not obvious, right? Why should you expect that either it's log n or it's n, nothing in between? That's really the punchline of this. Because there's so many non-trivial functions sitting between. Yeah, okay.
And how one can think of this in this like
I don't know how people
yeah.
conjectured and then they must have see lots of these log n show up because of the exponentiated inequalities. So that log n is not very mysterious. And also it's not mysterious that as P is large enough, you should get an order n component. It's also not very mysterious. Why there is nothing in between?
Yeah.
That is something people must have just worked hard and find it out. So that mystery, I don't know. But at least at the two ends, that most clusters look like log n, that's not too difficult. Okay, so is the Pranshu, is it clear what we are trying to do now? We'll be doing this one step at a time. Each step is more or less you have done most of the homework. So step number 1. What do I want to do? It's very similar to lambda. It's lambda greater than 1. A equal to A times log n, where A is equal to that 1 by, remember I lambda from last time, which is equal to lambda minus 1. So what we showed last time was that if A was greater than 1 by I lambda and lambda was less than 1, the size of the largest connected component was less than log. Now we are going in the supercritical region. That's time to lambda less than. Then that greater than n. This is explicit for that little of one. That's what
No, we have so.
we are going to show this, but all the work is done. It's going to simply follow from the stochastic domination from both sides. One we did above, one we did below. From above we'll get one answer, from below we'll get another answer. Both of them will have the same epsilon xi lambda. It will have one smaller component, other large component of the same order. That's all. Okay, so can somebody give me the proof? At least on the above side, so it's at most less than equal. We did it last time. What was our stochastic dominating process compared to the Ardashani graph? Just simply P and P, right? The branching process with binomial n common P. We showed this stochastically dominates this process. This process dominates this process. We showed that. And from below, the branching process with binomial n minus k common P. That also we showed. So this was from below, that was from above. Where k is the system, you can put a q.
Okay, yeah.
Okay, so that's all really one needs to use to show this. And remember, this binomial process is very close to the Poisson process. It will happily go from one to the other. That also we have shown. So what does domination mean? Domination means is that the probability that less than equal to probability P function. This we already shown that the branching process, the binomial branching process 1 comma p is this is the relationship between a Poisson and binomial process, and this is coming from the dominance, which is also very shown. Now, and how much is this? But now all I want to do is to somehow relate this quantity to the complete matrix on one side. So what kind of events are included in T greater than Kn? Kn plus 1 and so on. In particular, the infinity also is included, unbounded. So can you separate the two and say something? If the event that T is unbounded, plus T is bounded, Kn plus 1 and so on. The probability clearly is composed of these events, either it's unbounded or it is Kn plus 1, Kn plus 2 and so on. Okay. So which probability do you know as function of epsilon xi? What is the probability of something equal to xi? T is the total progeny size, remember? So what is that? Xi equal to probability of what? As a function of T.
No, xi into n is gives it.
There is no n. This is only a branching process with a Poisson parameter lambda. That's it. So there is no n. T is just the total progeny size of this branching process. So what does xi equal? The probability that T is equal to infinity.
Yes.
Yes.
So what is remaining there? All you have to do is to bound that remaining. The probability T greater than Kn includes this event plus many other events. What is the probability of those many other events? That's all you have to bound.
No, what do you mean by many other events?
Which are all the what is probability of T greater than equal to Kn include? What possible events are included in this? Kn plus 1, Kn plus 2, there's so many of them. All I know is just one of them, then it is unknown.
Okay.
So I have to count everything else also. What is probability of C greater than 2? That probability is 2, plus probability is 3, plus probability is 4, and I tell you probability of 10. But I also have to handle everything else. One thing is like greater than equal to. But we did this, you guys don't remember. So equal to lambda T equal to infinity plus Kn. This probability we have computed. Because the Chernow bound is the distribution of a Poisson random variable, Poisson branching process. We exactly calculated this. So I'm going to just state it and that is just simply this probability. This probability. This probability over here is nothing but order into the minus. Remember Kn is A log n. This we've done many classes ago. The probability that Poisson branching process the size greater than Kn but finite. We computed exactly. So what is the end result of all this? I get this is my xi plus order n to the minus ai lambda plus order Kn by. This is what I really want. So everything is here. This is how small is this compared to Kn by n? Is it smaller or larger? A is
Okay, I think it's smaller.
Kn by log a.
Yeah.
So this is smaller, so this is calculated. So I get
Just only.
less than equal to I get. Now I have to show it's greater than equal to us. For that, I will do the process from below. It is slightly more complicated because I have to include this Kn inside. It's not simply as nice as binomial NP. So slightly more dirty now. Let's just do this next part. Let define lambda is equal to lambda. Then because of my domination, so P of C of E to be given that Kn is greater than P of n minus Kn of Pn lambda by n. P lambda n. Okay, this is by domination, and this is the connection between the binomial process and the causal process. Where I written lambda n precisely in that form. All this dirtiness is needed only because I don't have a nice lower bound. I need to insert this over here. Okay, so now what can you say about this? Something similar to last time. What has changed compared to here? What has changed? This was P lambda C greater than Kn. This is P lambda n, P lambda n greater than Kn. So lambda n is substituted by lambda n. That's the only change really. Why would you get xi lambda n? What about the rest of the things? Everything will get substituted by lambda to lambda. So this you can show is little lower. This will dominate. Not important. But the bound I want is xi lambda.
Yeah.
Currently I have xi lambda n. How do I go from this to minus? Okay. If you can give me an argument, I will accept and do it. Just think what is going on. As n goes to infinity, where is lambda n going to?
Lambda.
So xi of lambda n should go to where?
Xi lambda.
So now just make it regress.
No, it doesn't.
That's all you have to do. There will be a little bit of slack, and that slack will be exactly of this order again. It won't be exact. So what I want to show is that somehow xi lambda n goes is equal to xi of lambda plus this term. That's all I want.
Yeah.
I want to write it as xi lambda plus another order k over n. That's all I want. If I can do this, then
Why interest in infinite arithmetic now?
no, but I'm doing everything for n, right? Since I'm looking for a bound with respect to n, I have to compute how much it is. As n goes to infinity, yes, you're right, it goes to 0. But how does it go to 0 is the question. Because I care about how large this component is. If I didn't care, then you're okay. I care about at a particular value of n, how large does it be?
With the change of variable in terms of.
See, lambda controls epsilon. It's a very complicated function. Eta is equal to 1 minus xi. That much means. If you can show something for eta, that will carry over to xi. Eta is the extinction probability. And this is survival probability. They are 1 minus of eta. And remember, lambda is greater than 1. Greater than the supercritical.
Eta is basically 1 minus lambda, right? Extinction.
No, lambda is nothing to do with it. Extinction probability and survival probability are 1 minus of each other.
Yeah.
Lambda is just a distribution parameter. So you would,
sorry.
you would expect the process
Yeah.
as lambda n goes and increases, it should look like the process with lambda itself. That's what the whole point. So L eta lambda n should look like eta lambda itself. Okay, so. You know, mean value here. What does it tell us? Anyone tell us? 10, 11, 12. Okay, what I want to write in terms of etas. Eta lambda n is eta lambda plus lambda n minus lambda d by d lambda of theta lambda and lambda n star for some lambda n star. Lambda n. This is true from the meter. So now can you say something? How large is the cat? Can I bound this? We did this, we looked at a derivative. There was one good reason for looking at a derivative of this extinction probability. You would have thought one more expression to compute. How it will come useful later. So that's why it is actually useful. You can look at it. It's first of all different. So that is easy. But then what the derivative itself was, if you don't remember, I asked you to look back at it, but essentially what you can learn is that this is at most. The second term is at most. That's precisely the reason. You would like to compute the derivative. The derivative is exactly given if you want to look in the notes also. So now xi is nothing but 1 minus theta, so I can exactly get this. This is true, this is true. So actually, I get what I want from both sides with just a different order terms. What did I do? It's very simple proof. On one side, I controlled the Poisson process with just parameter lambda from below at n minus kn comma p, which is the next one. Essentially lambda n rather than lambda. This was above, that was below, and both of them are compressing it with the same rate. Only difference is in the orders. That tells us that I can control the probability that the connected component of any one particular node is greater than kn, where kn is behaving like a times log n. Okay. We'll be able to do one more step and then. So only small things like computing the derivative will eventually come in. If you can say some interesting properties, some recurrence relationship, you never know how it will come. Especially derivative, because you also always want to look at first order approximations of things. It's always very useful. Possibly with second. Okay, so let's start now. And towards that, we control the variance of this quantity z greater than equal to k. So let phi is then k lambda the expected value of C of v given the indicator that C of v that's the condition on the fact that the connected component condition on the fact that the connected component of this node V is less than K. What is it actually like? Okay. Sorry. This is the connected component of V has size at most K. Strictly less than K. Under that conditioning, what is the acceptable value? Lemma. Remember that greater than K.
Yeah.
What was it? Just for
Sound of the lower organs
some our indicators are P of B greater than K. B. Okay. So lemma is variance of Z greater than that most standard times theta certain n times this quantity. Right. So can you interpret this as what is going on? This is the expected size of the connected component of B given that it is smaller than A. What does it have to do with the region of the system?
Yeah, your question.
Why should we expect something like this?
Z and Z X squared.
They're related.
They should be related, right?
No, that's not just fine, but why should you expect something? What is going on?
N
Times.
Hmm.
So how much is like what is the interpretation of this? This is roughly
For all the nodes, right?
yeah. So if you want to sum this up,
Yeah.
that's what you'll get. What about this? Why is it multiplied by lambda k plus 1? And why variance a function of this at all? Variance means the variation like this how large it can really be compared to its mean. That's what really variance is. So it's not very well behaved. So you always want to control variances to make sure that the random variable is not badly behaved.
And what was the mean of C?
Mean of C. What is C?
No, no, it's Z. And
Pi. The top one.
No, no, zero.
Mean of Z is the expected value of Z, which is how much? Xi. Times n.
Yeah. What is it telling me?
Expected value is nothing but n times. Telling you that compared to xi n, how much it varies really. So is there a way to interpret this?
Expectation of that.
This is
Minus the expectation.
n times.
Yeah.
That's the expected value. This is telling you that with respect to the expected value, the variations is at most this large. You would like to be as small as possible.
Yeah.
So why is it coming out as a function of this? Is there a way to see this?
Do you expect that this right hand side should be a small quantity?
So that we will see how large it is, but think of a connection between variance of Z greater than K and chi. That's all I want to ask. I don't really think exactly this. formulas. Why should it even depend on that question? Okay.
Any variation in the GK would only come from the circle below it.
No, say this clearly.
Any variation in Z greater than equal to K would come from the number of nodes which belong to clusters of size less than K. Right.
To make it more precise, I see what you're trying to say. That if that is large, let's just think of that way. Suppose that is large, why should the variation be large? Let's just see that. There's no reason, right? All I'm being told is that below K, but if the expected value is large, why should it matter to this? I'm just being told, the information being told here is that it's below K. Now, if it's large or small, why should it affect the variance of Z?
Okay, yeah, so it should not.
The way to see it is the following. Why should it really matter? So think of the probability. Mod C of I is less than K. Okay. Mod C of J. So J and K are different vertices. Should avoid it K, but this one follow. And there is a connection between the K and J. What is it telling you? That the connected component of I is less than K, connected component of J is less than K, and I and J are connected. That's what this event is.
Okay, yeah.
I'm just trying to see why it should like this quantity should ever come into the picture. Think of this event. Clear? So there is an I, there is a J. This guy's connected component is at most K. This guy's connected component also at most K. And there is somehow connection between this. This is what the event is. That's the event's probability I'm trying to compute. What can you say about chi in this regard? Is there anything which? So when I is connected to J, what is the relationship between C of I and C of J?
They are in the same one.
That's the critical thing where it will show. This is nothing but maybe probability that C of I is less than K because they're identical. And I is connected to J. And this is also equal to the expected value, the indicator. I can do the same thing with the indicator. C of I. I'm going to go below. Can I say expected value of this times expected value of this?
Are they independent?
We can break it down. If J belongs to G,
Look at the kind of event chi is. Look at the expression chi is. There is no sense of independence.
Yeah, it's a conditional.
But so you don't have to really not even true, but you don't even have to break it apart. But something you can do
In terms of
bias.
yeah.
What can you do? That's the real reason why variance depends.
So now this integrated to from I to J. I mean, you can basically J can be the all the nodes to the in the component, right?
Yes. Carry on. They can go from like essentially all vertices.
Yeah. So if you take the sum of this,
If I sum this over all
J
ij comma n, ij belonging to n,
and
because that's what really the progressive will work. For the moment, I've just looked at one I and one j.
and then you'll get back the
No, so this will be ij belonging to n.
yeah.
I can do this summation over ij. Now I can say I here and j inside. That much I can. This I can do.
Yeah.
Now can you do one more step? Okay, something like that.
Okay.
What does this mean?
Yeah.
Size of the connected component of I.
Yeah.
And this is condition that C of I is less than equal. That is precisely what the quantity variance.
Yeah.
Yeah. This is expected value of C of I. One. C of
Somewhere
no, I can produce this inside. Because this is for one particular vertex. So now. Yeah. So this is, and the law is the same, so I'll get n times of this.
Yeah.
So this is one n times. So this is how chi enters. Now tell me why is this event useful to compute the variance? So this is slightly more complicated. This is clear.
Yeah.
If I were to compute this, and this was very important, but if I has a connection to J, these two quantities are essentially identical. That's why I can proceed. Now think of this event having any connection with the variance of Z greater than K or Z less than K. They're equally good. Either look at Z greater than K or the complement event, Z less than K. If I can control that, that's also okay. So what is variance of Z less than K? So Z less than K is what? Equal to 5. We have defined Z greater than K. I can equally define Z less than K. Now what is variance of Z less than K? Brutal expansion. They're essentially equal to. These are all nodes whose connected components of size less than K. So I can write this as I comma j. I less than K. P of j less than K. Less than K. I close to j. Plus everything the same. This is the first term. How much? What do I need to subtract?
No, wait.
I'm just writing the variance.
Yeah.
This is not complete. This I have just taken into two possibilities of the first term variance. I have to subtract something out. Subtract the probability. That is C of I less than K.
What is the second one? Everything?
This is
No.
this one, right?
Yeah.
This is exactly the same dot, comma, I doesn't have a element. Coming over
Okay.
all possible pairs ij. Either ij are connected or they're not connected.
Yeah.
I'm just writing the sum in a expanded form. I could have simply said just this. This is how the first term is what we actually computed in the previous. What is the probability that two nodes I and j have their connected component size less than k and they have an edge connected. And this is the reason why this chi enters the picture. Because chi is nothing but a function of two nodes having connected component size less than k and having a connection between. That's the reason this guy. The rest of it is slightly ugly computation to make.
Can you know the variance definition?
Variance definition typically is simply variance of x. X minus
That's like this.
nearest to that minus. Right. You open, so this is sum of indicators. This is what will end up coming. So z less than k is nothing but sum of indicators. You open them up, you just simply get pairs of this type.
Yeah.
And each of them are nothing but expected value of indicators and their probabilities. The only thing I'm really doing is to break them up into two classes. One having an edge and one having no edge. Now, without this edge is what something I have to compute separately. With an edge, I already computed. And this is the reason why the chi enters the picture. So let's just finish it. Otherwise, we'll have to build up everything. Okay, so what am I after now? Probability. C pi is less than k. C of G. So I'm going to open this up. Even. Just opening the joint probability. P of x comma b comma c is p of a times p of b given a times p of c given a comma b. So this we will just cover one by one. Every probability that. And let's also write just for notation is as what can we say about this? Now, the new condition is that I is not connected to J. So, what is the probability that the connected component of I is less than N? I is not connected to J, and connected component of J is less than K. So, this guy is the connected component of I. This guy is the connected component of J. I and J are not connected. So, if this is less than L, what information am I going to get about C of J?
And I and J are not connected.
I and J are not connected.
Couldn't it just be independent?
Okay, that is not bad, but what more?
In minus one.
Yeah, so how many vertices on which this independence remains? How many have been eaten away?
L.
So N minus L. So you should really think of the new graph, which is only n minus n vertices, where j is part of. Okay. That's really what that probability should look like. This is probability n minus n what? Yeah. This I repeat as it is. Now what more can I do? Suddenly I have now this P of n minus L. I would like to get rid of that. So otherwise all my computations are over n. Now you're bringing in n minus L comma P. So what do I have really? This term in terms of P of this times P of n minus L comma P. This is what I bounded by 1. Yes. What can I do? What? So think of, so what is this n minus L graph with P and G of NP? How is the related? This is what is going on, right? This quantity is nothing but a graph over n minus L nodes, the probability P independently formed. Everything else is over G of n comma P. So it's a bigger graph. Is there any relationship between these two graphs? We did something about monotonicity. That if P increases, so G of n of P1 and G of n of P2, where let's say P2 is greater than P1, what is the relationship?
N was greater than n minus.
No. So in this case, it's n. I'm just trying to recall n of P1 and G of n of P2. Yeah, and P2 P2 was greater than P1. We said something that this is there is a coupling which is monotonic. Whatever happens here also happens here.
Yeah.
Now if you take the second coordinate, that's what happened here. You change n to n minus L. What do you expect to happen?
We just this goes into pi over n.
No. So in this spirit, what's happening in these two graphs?
So the
P is the same, the number of nodes are less. So size of the, let's for example, take example, size of the connected component. Which do you think is going to be having a larger connected component?
and of course the largest.
Right, so you can also have similar monotonicity as when we went from changing the second component rather than the first component. So any interesting relationship you can tell me between G of n minus L comma P and G of n comma P? Or can I, like, if suppose I wanted to construct this from here, what should I really do? This is a nice way to construct a copy of this, right? So suppose I build this, what do I need to do to get a copy of this? Copy means an identical copy in distribution. I could potentially add how many nodes? n minus L is and pick anybody and just map it to pick any node here and pick any node here and attach them with probability P independently of everything else. I will get a copy of this. So, what can we say about such a graph?
What can you say about the graph?
Any interesting relationship between G of n minus L comma P and G of n comma P? Essentially, in terms of a connected component, so suppose there is node 1 here, C of 1 less than 3, and C of 1 less than 3. What can you say about the probability in this graph of this quantity and probability of this in this graph? One direction is less than equal to 0.
Yeah.
You subtract it out and tell me how much that probability looks like. So I'm asking you to subtract this probability. So subtract this probability from this probability. This is larger.
Yeah.
This quantity is larger because the graph is smaller. So think of probability of C less than K minus, so this is my n minus L comma P graph minus n comma P C of 1 plus. The natural quantity to think of it. Graph has somehow shrunk. The number of nodes here is less, but everything else is identical. So I can think of this product. But if you have this interpretation in mind, what does it actually mean, subtracting this? So is it equal to with respect to L comma P to be less than comma C of N P.
No, I don't understand what is it.
I'm writing in more compact form the difference of these two probabilities.
Yes.
This event is that with this my smaller graph, the connected component of node 1 is less than Q.
Yes.
This event is the larger graph, the connected component with n comma p is greater than P.
And you are claiming that this is equal.
Correct. So this is a complement event. So if you want to induce it, it's a minus sign here.
Yeah, and that.
Right. Now you have to show that this is actually true. And the way to see it is by just constructing this coupling.
Okay.
That how are these two connected really? They are connected via creating an extra number of L nodes and connecting any two inside with a edge with probability. Okay, let's stop there. Try to see if we can do this.